When you update your profile picture or refresh a timeline, the response feels instantaneous. The internet seems like a flawless, smooth surface that just works. But underneath that glass screen, the physical reality is brutally chaotic. Petabytes of information are moving across thousands of individual servers. Hard drives are constantly degrading, network cables drop packets, and memory modules randomly flip bits. To keep that chaos from crashing your app, engineers use a concept called abstractions. They stack layers of software on top of each other. Each layer deliberately hides the messy, unpredictable physics of the layer below it, providing a clean, simple interface for the layer above. It's tempting to get caught up in the latest industry buzzwords like web scale or big data. But to truly understand how modern architecture works, you have to dig past the marketing. We have to descend through those layers of abstraction and look at the physical trade-offs engineers are forced to make. We experience perfect reliability only because engineers maintain an elaborate lie, a facade sustained by constant software intervention against inevitable physical failure. The very first layer we hit is the data model. This is where messy, complex human realities, like who you know, what you bought, or where you live, are forced into strict digital formats, so a computer can actually process them. The relational model locks unpredictable data into strict tables, keeping predictable transactions organized. Conversely, document databases treat data as self-contained files, sacrificing uniformity for massive flexibility. But if connections matter most, a graph model is built entirely around tracing the relationships between entities. There is no single correct way to organize this information. Each data model is just a specific lens. Engineers pick the one that best manages the specific type of chaos their application generates. Once the data is organized, we hit the next layer down, the storage engine. Here, abstract ideas are physically written onto a spinning disk or flash drive, stored as tiny magnetic charges representing ones and zeros. At this level, architecture faces a physical tension. You can optimize storage to quickly write millions of small, random user inputs as they happen, what we call online transaction processing. Or you can optimize it to scan massive historical columns of data all at once for deep analytics. You cannot maximize both on the exact same hardware. To maximize physical space, human-readable information has to be aggressively stripped of its context. The computer packs the data into dense byte sequences, cutting out anything that wastes storage capacity. This encoding diagram shows how spelling out username repeatedly wastes space, so the engine replaces the field name with a numeric alias, field tag 1. To avoid scanning the whole drive later, the database uses byte length markers to jump directly to the text's location. Storage engineering is a zero-sum game. The time you spend carefully compressing and indexing data right now slows down how fast you can write it. You willingly sacrifice write speed to increase your read speed later. Eventually, an application scales beyond a single machine, distributing data across a network of computers. This is where the physical reality gets truly chaotic. There is no such thing as a perfect network. Signals experience unpredictable delays crossing fiber optic cables. Hardware silently rots. And because each server has its own internal quartz clock, the timekeeping on these machines is constantly drifting out of sync. This creates a massive engineering challenge called consensus. You have multiple blind, deaf, and occasionally failing machines, and you have to force them all to agree on a single, exact sequence of events, a concept known as linearizability. In a two-phase commit algorithm, a central coordinator asks every machine if they're ready to write data, waiting for every single green confirmation before locking the transaction. But if even one node drops off the network, the entire system halts to prevent corrupted data. Down at this physical layer, engineers cannot defeat the laws of physics. They only have the choice of how their system will fail. When the network breaks, they have to decide if the application will sacrifice perfect data consistency or sacrifice its availability and go offline entirely. Pulling back up through the distributed networks, past the storage engines and data models, we arrive back at the surface, that bright, clean user interface. A flawless timeline load requires a hybrid approach. Modern applications survive by layering multiple specialized architectures to manage different fragments of the chaos below. This engineering practice is called polyglot persistence. A company might use a highly rigid relational database to handle their financial billing, a flexible document store to hold user profiles, and an asynchronous stream processor to track real-time clicks. They stitch these distinct tools together behind a single API. You will often hear industry hype about a universal database that claims it can scale infinitely and process everything. But any system claiming to do it all is simply hiding the structural compromises it made down at the disk layer. Specific coding languages and tech marketing trends will eventually fade away, but the absolute physical constraints of data and the mathematical principles engineers use to abstract them are permanent.